Monday and Tuesday. Monday's lecture is available through Canvas and through VidGrid. All lectures will be recorded, so keep that in mind. Again, if you ask a question, your voice might be picked up. If you come up here towards the beginning or the end, I'll try to cut those out so that nobody shows up. But if you come up in the middle for whatever reason, understand that you will be on camera. And of course, they are recording back there, but for a different thing, and that will not appear on YouTube or anything else like that. Make sure that you are getting lab. If you got a message from me because you're new or you didn't get credit for Lab 1, make sure that you are completing that by tomorrow to receive credit for Lab 1. You definitely need to do that because you need your login for this course. Okay? So we're going to go ahead and get started with the actual course material today. Remember, you do not have class on Monday because of Labor Day. So we'll try to get through as much as we can for your next lab, which is going to be basic variables, using variables, and basic input and output. But before we do that, I want to, if you did go through the lab on Tuesday, and if you watched what we did on Monday, we went through the process of creating a program, compiling it, and running it. The actual process is a lot more detailed. So I want to actually look through that process and look under the hood a little bit, just for some perspective. Source files, a program begins as a source file. A source file is a plain text file. All right? It's containing computer code in a high-level language. It's not necessarily English. Again, that's Star Trek kind of stuff, where you'll be able to program a computer by just simply telling it what you want it to do in plain old English. Computers don't understand English. In fact, if you go back to the very beginnings of computers didn't even understand high-level programming languages. You actually had to literally program in binary. You had these punch cards, and you'd punch it for a 0, or you'd leave it unpunched for a 1, or something like that. You actually had to write your program in binary. You had to be the compiler. This is 1950s or whatever. And then along came assembly. Assembly is a programming language. It's a low-level programming language, but basically it's the language of the processor itself. You can do things like load up this value into this register, load up this second value into the second register, compare what's ever stored in register 1 to register 2, and if they're equal, then go to register 3 or something like that, right? Very, very low-level kind of stuff where you're actually telling the physical hardware what to do. The physical hardware is nothing more than a circuit. So if you're an EE or if you depreciate this, it's just a bunch of gates, a bunch of AND or NAND gates, etc. So you have to speak its language. You have to be able to say, load up this thing into this register and jump to this memory location, whatever. And so that improved things because at least you weren't going in binary anymore. At least you didn't have a punch card to say 0, 1, 0, 1, 0, 1, and then that's your actual command to the computer. Even though assembly was an improvement on that, you still were forced to think like a computer, that you had to think in terms of registers and values and jumps and stuff like that. So along comes a higher level programming language like C, where it looks kind of like English, right? If we look at the Hello World program, here's one, then we can read this at least, right? It's not just a bunch of register 1 to register 2, register 3 to register 4, right? We've got plain old English here, include, right? We have a meaning to that. Main, printf, right? It's not 100% English because I'm not saying print the words hello world followed by an end-line character, but it's much closer to English than assembly is, right? So how do we get there? How do we go from this? How do we go backwards? How do we go from this high-level programming language like this? I'm going to go ahead and increase the size for everyone and increase this over here. How do we go from a high-level programming language that looks like this to something that a dumb computer can understand? Well, the end product of a program is an executable. Source files have to be compiled into an executable program. And an executable program is nothing more than a bunch of binary, a bunch of zeros and ones that the actual hardware can understand. And when you do this process, you have to do this process for a particular system. If I take that C program, that Hello World program, and I compile it for my Mac over here, that produces binary that this Macintosh can, this Mac computer over here can understand. The hardware, the operating system that's running on it, only it understands it. If I take the same program, or if I take the executable from my Mac over here and I put it on one of your Windows machines, it will not understand it. It won't run because it hasn't been compiled for that system. But if I take the source code and you have a C compiler on your Windows machine, and I compile it for Windows and for your particular hardware, then it'll run and perform and pretty much do the same thing, right? So going from a source file down to something that the machine understands, that process is called compiling. And in fact, it's a lot more complicated. Source, there we go. So what does it look like? You go from source to assembly to machine code. There's actually a few steps in between where you're actually linking in with the standard library and stuff like that. So what I want to do is I want to give you a demonstration. When I showed this to you on Tuesday, all I did was one simple command, GCC, and it did all of this stuff for me. It did this entire building chain in one. What I want to do is I want to break this down into a step-by-step process. And to do that, we're going to start where we did before. We are going to start with a source code file, hello.c. And I'm over here on the CSC command line here. And we'll look at that again. What does that look like? Well, there's my header comments telling you what this program is. Some bad white space there that got transcribed. There we go. Everything's fixed now. I'm bringing in some standard libraries, some standard input-output libraries, so I don't have to reinvent the wheel. I've got this main function here. That's the main entry point, and we'll talk about that later. And then I've got this print statement that simply just says print hello world followed by 3 exclamation points and then an end-line character. Let me go ahead and increase the size here so that you can see it a little bit better. All right. So that's my starting point. I've got a source file. What I now need to do is I need to assemble it. Okay? And what I'm going to do to assemble it is this command. It is gcc-s hello.c. And let's see what that produces. Yes, let's save that file. gcc-s hello.c. Right? And remember, no news is good news, right? There's nothing wrong with our program. And you see that it produced this file right here. Let's take a look at what that file is, or what's inside that file. Right? Certainly not as readable as that C program. That C program was high-level programming language. Print this thing, print this message, right? That's all that needed to be said. But if you're actually going to run it on a piece of hardware that a dumb machine needs to understand, wow, it blew up. There's a lot of stuff here now, right? Much longer program, right? And you can kind of read it, right? Well, hey, there's our string, right? That's a string of characters. And then you can kind of read these commands, move Q, sub Q, move L, right? You can kind of call puts, call this other function called puts. And so you can kind of read this stuff, but it's way less readable, right? That's because it's assembly language. It is a much lower level programming language. That's what GCC is doing automatically, by the way. Then what GCC does is it compiles it, right? You can compile it using this C flag. Let's do that. I'll get out of this. In fact, there's a utility on Unix that you can ask what kind of file this is. Let's ask what kind of file hello.c is. Whoa, it's a C source file, right? And what kind of file is hello.s? It's assembler source file, right? It knows these things. Now let's go ahead and compile it. Hello.c, right? And again, no news is good news. What it did is it produces this object file, the .o file. .o stands for object. Let's try to take a look at that. Emacs is a text editor, so let's try to take a look at the contents there. Now, is that readable at all? No. Again, we're going from a high-level programming language down to assembly, which is still kind of readable, but still way more computery. And now we're at the level, basically, of pure computer language. It's not plain English anymore. It's just a bunch of zeros and ones. Now, some of this stuff is readable, ELF. All right, I don't know what that stands for, but you can kind of, oh, hey, there's our string, right? Because that is a readable string. But frankly, the rest of this stuff, most of the rest of this stuff is just garbage to us. It's not garbage to a computer because computer understands this language, this binary language. It produces a hello.o object, and we can look at it a little bit better. We can format it a little bit better. Hex dump hello.c, .o, right? And then it'll try to format it a little bit better. This is all just binary, but it's transcribed to a hexadecimal. What's hexadecimal? What's binary? So we as humans have 10 fingers and 10 toes, at least the luckiest of us, right? And so we've got 10 fingers and 10 toes, so we count in base 10, decimal. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we start back at 0. A computer doesn't have toes, doesn't have fingers. What does it count in? It counts in high electrical charge, low electrical charge, on, off, signal, no signal, or pit versus rivet, right? All of these binary, a 0 or a 1, and that's all it understands. When it goes from 0, then the next number is 1. Well, what happens when you go from 9 to 10? Well, you add another 0, and then you go back to 0 over here. So 0, 1, right? What happened? 1, 0, sorry, mirrored over here. And then what's the next one? Well, you add a 1. And now what's the next one? Well, you add another 1, but well, you've got 1, 1, and that's all you've got, zeros and ones. So it becomes 1, 0, 0, just like you do in decimal, right? This is hexadecimal. It adds in 16 characters instead of the usual 2 or 10. It adds in 0 through 9 and then A through F. So it's base 16. You can do this with any base. Typically in computer science, we use binary, octal, of course decimal because we're humans and we like to read things, hexadecimal, which is going to be base 16. And you can go above even more than that, base 128 or base 256 or something, right? And it's just a different way of representing numbers. 0, 0 is still 0. 0, 1, that's 1, right? 46, that's not 46. I don't know what let's see. X46 to decimal, what would it be? Duck, go, oh, okay, there. It'd be 70. It's not 46, it's 70, right? That's the equivalent of hexadecimal. But it's still a low-level computer language. We kind of see some things that we understand, again, like hello world. But otherwise, all these dots are just things that cannot be represented using plain text because it's not plain text. It's a bunch of zeros and ones, right? So the process so far has been to assemble it into assembly language, compile it into an object file, and again, that produces an object file called hello.o, and you can actually view it if you want to. I used a utility called hexdump to make it look a little bit better. And then the last step is that you also need to link in external libraries. Sorry, it's not snapping like it should. Linking in, over here, my program does not contain the code to actually produce output, right? That is contained in, where was that again? Hello.c. Right? I brought in these external libraries, the standard library, stdlib, the standard library, and the standard input-output library. Right? I brought those in because I did not want to have to reinvent the wheel. I didn't want to write my own print functions. I'm going to use the standard input-output library print function instead. That's not part of my program. If we take a look at the hex dump again here, there's no function to take care of that. That function is located in another object file. So I've got my program, which is an object file, that library over there, which is an object file. I have to bring them together in order to produce an executable file. I have to link them together and then finally produce an executable file. And to do that, it's a little bit more. It's another process, but basically I can go gcc hello.o, I think, and it'll produce an executable file. That executable file already existed though, and now I can actually run my program. Hello world. So this entire process was all completely opaque to you. You don't have to care about it, right? You can do it all in one step, right? So all at once. Well, it's what we did yesterday. It's just simply gcc hello.o, or c, sorry. There we go. There. If you don't want to do that entire process all in one shot. Now, you might want to do that process piecemeal if you've got a more complex project. All we have here is a hello world program, right? There's not much to it. You can go ahead and compile it with one line. But if you've got a huge, complex project with hundreds of different source files, dozens of different external libraries, and a bunch of other different artifacts like, say, image files, icon files, and all that kind of stuff, then you need a much more complicated build process. And towards the end of the semester, we'll start to view how you can do that with a much more complicated project. You need an entire other language called a build system. And our language that we're going to use in this course is called make. And as we'll look at what are called make files. But I just wanted to give you that perspective of what that might look like. Now I want to give you another program. Right? So that was a Hello World program. All it did was say, hello. Here's our real first program. In fact, let me update the date there. It's no longer, not that one. What is the date? It's August 28th, 2019. There we go. And again, it's not snapping, sorry. In fact, it's so large, let's go ahead and zoom out here so that we can fit it all on one screen. There we go. So what is this program? This is a much more substantial program. It's still a very simple program. Tell me what it does. Okay, how did you do it? Did you read all 20-some lines to determine that? No, what did you read? You saw the word mile? There we go. You read that one sentence, right? Gee, that sentence turns out to be pretty damn helpful, right? That's called documentation. Telling other people what your code does saves them the need of having the cognitive load of having to read every single line in your program. And then once they've finally read the entire thing, now they finally understand what it does. Documentation relieves other humans of the need of reading through everything to understand what the purpose of what you wrote is. Right? And so I've got documentation at the top. It says who wrote it, it says when they wrote it, and it says what this program does. For your first few assignments, this is what we're getting at when we talk about documentation. Later on, when you write a function, that function needs to be documented. What does this function do? What are the expectations of this function? What output can I expect and what output does it expect me to give it? Right? But otherwise, this program converts miles to kilometers. Right? Not earth-shattering, but at least it's something more substantial than just saying hello world. Right? So let's walk through a couple of these lines here. The first two lines are going to be familiar. That's bringing in the standard input-output library and the standard library. You'll note that I did them in a different order and with slightly different white space. Generally, white space doesn't matter. Let me go ahead and be consistent about my styling, though, and do what I did before and put a space in between those. The space doesn't generally matter, but what does matter is consistency. Whatever style you use, stick with it. You should see the same white space at the top of your program as you see at the bottom of your program. You'll note that the main function here is we indent all the contents of that, right? Well, I didn't indent, two spaces on the first line, 5 spaces on the second line, and then 1 space on the third line. I indented at the same level for everything. I am consistent about my styling, right? So that it is more readable, okay? We've got something here that define. Okay, well, I can read that. KMS per mile. What do you think that is? How many kilometers are there in a mile? And it turns out that there are 1.60934 kilometers in a mile. Right? So that's our first number here, the first number that we actually have in a program. It represents the number of kilometers in a mile. How do we know that? The name right here. Another aspect of programming is writing clearly. You want to make sure that all your variable names represent, or you name your variables what they represent. If I named, this is not a variable technically, we'll talk about the difference soon, but if I named this my awesome variable, right, would that be very descriptive? You'd have to look 1.60934. What the hell is that? That's just, we call those magic numbers because they're pulled out of thin air if they don't have a description, right? 3.14159. We would all understand that as pi. 2.71, we'd all understand that as e. 0.1234567891011121314. Do we all know what that is? That's a Champernowne constant, but who cares, right? That's way more esoteric, right? That's why we want to make sure that we name our variables. Would you label a variable that represented pi as x? Right? No, you'd call it pi because that's what it is. Well, you want to label this as kilometers per mile because that's what it is. Right? That's what it represents in the real world. We've got, now on the next line, we've got a main. Now this is the main, and every program has to begin somewhere, right? So where is it going to begin? Most programming languages have the concept of what's called a main method or a main function. Here we've got a main function. That when you start your program, it's got to start somewhere. Where does it start? It starts at the main. You could have other functions like printf or scanf that we'll see here in a second. You could call mathematical functions like square root or pow, which is taking the power, x to the y. You could call a bunch of other functions. You could write a bunch of other functions. But the function called main, that's the starting point of any program. Okay? Don't worry about this stuff for now. We'll talk about command line arguments later. Then what I've got here is a couple of variable declarations. What are they? What do you think those variables are intended to represent? Miles and KMS. KMS, what is that? Kilometers, right? So I'm kind of violating a little bit of style here because for the first one, I didn't abbreviate that, did I? Let's try to abbreviate it. What would it be? MS. What's MS? Microseconds. That everybody understands that MS to be something else. That's why I wrote out miles. But what about KMS? In the context of this program, when we're doing distance stuff, pretty much that's going to be universal. So if the abbreviation or the acronym is understood within the context of the program, it's okay to use the acronym or the abbreviation. But if it's esoteric, if it's highly specialized, then you probably want to write it out fully. You're not paying by the character. 30, 40, 50 years ago, they were paying by the character. Remember stdio? Well, why didn't they just write standard input-output? Why didn't they just write standard library? It's because 40, 50 years ago, if you could save even 1 byte of memory, you did it. All right? And that's why you'll see a lot of abbreviations that don't make too much sense or that are inconsistent. It's because way back when it mattered, it no longer matters today, but we want to make sure that stuff is still recognizable, and so we're still living with that. We're still to this day. We don't no longer pay by the byte. I've got a 0.5 terabyte storage on this computer alone, which would probably be more than all the storage capacity of 1962, right? Or whatever it was. This one computer has more capacity than all the other computers combined from 1960, even 3 or 4 or whatever. Right? We're no longer paying by the byte, but we still live with that fact to this day. Okay. C is old, and changing things breaks things, and you don't want to break things. You want everything to still work 30 years from now without having to rewrite everything constantly every few years, like, say, a JavaScript language like JavaScript, where, yes, their cycle is rewrite everything, throw everything out, rewrite everything every so often. C is different. C is old, and it's got to still work. What's this right here? That is a comment, also part of documentation. It tells you my intent. What am I going to do here? I am prompting the user for some input. Even if you don't know any C, or what the heck is printf, what's a string, the plain old English that I put into this documentation here, it tells you what I'm doing, right? And that's the intent of comments, that they tell you what you're doing, why you're doing it, and also be careful because of this. I did it weird this way because this system over here still doesn't work, whatever. There's a bug over here that I know about, and I'm working around it, right? Comments help you tell other people why you did something the way that you did it, right? This one, now in general, after the first couple of weeks, when you start writing more complex programming, I don't want to see a comment like that. If you know, once you know enough of a language, simple stuff like printf, well, I know what they're doing. They're printing this message. You don't have to say, I'm printing a message, and then also have a line, print message, right? You don't need to double up on that. That goes into the DRY principle, the dry principle, which stands for don't repeat yourself, right? If you can write one function that does one thing, and that you don't write another function called a different thing that does it slightly differently. You don't repeat yourself. You don't have a chunk of code here and then cut and paste it down here because you need to do it again. You take those two pieces of code and combine them into one thing and put it into a function. You don't repeat yourself. You reuse that function as much as you want. Likewise, in the context of documentation or commenting, don't document the obvious. And so if you've had years of programming experience, even if you've by the second week or third week, everybody will know how to use a printf statement. You don't need to document something like that. I did it here to show you what documentation looks like. This is not necessarily good documentation. Okay? Then I've got a printf statement, and we know what that does. That prints to the standard output. What is the standard output? Again, this is standard input-output. There's a concept of standard output and a concept of standard input. Standard output is the screen, your monitor, your terminal, whatever, right? We're not going to be dealing with graphical user interfaces until the very end of this course. But that's another form of output. You know, you see a pretty icon or you see a nicely formatted graph or something like that, right? That's a form of output, but that's not the standard output. The standard output is just a bunch of text on your screen. The standard input is what, for our purposes? What do you sit there and mash all the time? The keyboard. The standard input is going to be the keyboard. Of course, you have other input devices. I've got a touch pad here. You've got mice at home. You've got maybe a VR set, and now you've got input devices that know where they are in 3-space, right? You've got a lot of the Microsoft Kinect, right? Motion detection. That's input. It's not the standard input. The standard input is your keyboard. Okay. On the next line, I've got read the input, and I've got scanf, right? And then I've got a bunch of cryptic other stuff that we'll understand eventually. As a preview here, %LF stands for long float, and it's basically a double, right? Remember miles and kilometers? What we had another keyword that I kind of skipped in front of those. What is that? Yeah.
It like tells you what kind of input you're putting in, so a double means that you have like a
Double is a decimal value. Others would include floats, and I'll talk about those, but we're not going to use floats because floats suck. They only have about 8 decimals of accuracy. Doubles have about 14 to 16 decimals of accuracy. We're going to stick with 3 main variables at first. Doubles, int, which is not here, but well, it is here up in our form. Int, what do you think that's short for? Integer, whole numbers. Doubles are going to be floating point numbers or things with fractional values. 0.13, right? 0.5, 3.1415, right? So LF stands for long float, which is simply just another way of saying double. And so it says that we're going to read from the standard input, somebody mashing their keyboard, a number. We prompted them, please enter the number of miles. They can enter 52.1 miles. And then we read it in. The way that we do that is through scanf. So that's the opposite, the antonym of printf. You're not printing anything. You're scanning something. You're reading something in. And you're reading it into this variable. What is that ampersand right there? Don't worry about it for now. It has to be there. Scanf, it has to be there. Right? And we'll revisit that later on. This next line is probably the most complex so far that we've seen. KMS is equal to KMS per mile asterisk miles. So how would you read that? How would you, forget about the coding for a second, how would you convert miles, say 10 miles, to kilometers? 10 miles. You'd multiply it by the ratio, the 1.6 figure. So if I've got a variable that represents miles instead of a number, 10, and I've got another, we'll call it for a variable for now, a variable that represents the number of miles per kilometer, or number of kilometers in a mile, if I multiply them together, then I get a result. I get 16 miles, or 16 kilometers in 10 miles. Now, look at very, very hard on your keyboard. Do you see the multiplication symbol? A times B? No, why not? keyboard's way older than computers. The QWERTY keyboard was created when? I think in the 19th century, technically. So way before you would normally be doing multiplication stuff. Yeah, there is an X there, but the X is not that symbol right there. So what we needed to do is we needed to do adapt. And since there's no multiplication symbol on the standard QWERTY keyboard, why is it called QWERTY, by the way? Look at the top left. What letters are there? Exactly, QWERTY. There are plenty of other types of keyboards, Dvorak, or if you've ever seen some Asian keyboards, where Asian scripts have many more, like there's some old-style Japanese keyboards. There are 48 letters in the Japanese alphabet. They've got 48 keys, and then you're literally like reaching across the desk to type every single time. They never really caught on. We stick with the QWERTY keyboard. Since there's no symbol, we need to use something else on the QWERTY keyboard that kind of looks like that. And what kind of looks like that? An asterisk. Right? And there are other things that are not on the keyboard. Right? The standard division sign. That's not on the keyboard, so what are we going to use? We're going to use a slash instead. Plus and minus, those are on the standard keyboard. So if you want to do addition, subtraction, just go ahead and use those that are on your keyboard already. But the thing on the right-hand side is the actual multiplication. Now, this is not like algebra saying that A is equal to B times C. Right? That's an assertion that this thing on the left-hand side is equal to the thing on the right-hand side. Okay? That's not what this is. This is taking the thing on the right-hand side and placing it into the variable on the left-hand side. That's how it should be read. This is not algebra. This is programming. Okay? And then, finally, we have this print line. %f miles is equal to %f kilometers and the line. This %f and this %f are called placeholders. The first one corresponds to this variable. The second one corresponds to this variable. And if I had a third placeholder, and I'd have to provide a third variable, fourth variable, it allows you to print the values stored in variables. Remember, it's just binary. So if I were to literally print this out to the screen, it would just be a bunch of binary garbage. By putting this in a printf, F stands for format it. Format it in a human-readable manner. So convert that thing that's in binary and convert it to something that's in decimal, 3.14, right? So that I can understand it as a human, because you're a machine, you're serving me, I'm not serving you, right? So that's the purpose of this. And %f is very similar to this one up here, but %f is used in printf. Also note the difference here. I used an ampersand up here, no ampersand down here. Ampersand when you use scanf, no ampersand when you use printf, just because for now. I'll explain later. Right? It's memory management stuff. This is actually the memory address of that variable, and we don't need the memory address of this variable because it's passed by value versus passed by reference. Again, it'll all come later. Just for now, just because. Right? All right. So that's our first real program, right? Oh, and then, of course, at the end here, I return 0. Again, boilerplate stuff. Don't worry about it for now. Okay? So let's go ahead and run down and codify some of the things that we were discussing just now. And I'm really getting annoyed at this, that it's not snapping. So I'm going to do something really quick here to change. All right, bear with me for a second. Lectures. Basics, there we go, open with, marked to. Hopefully this will do a little bit better job of snapping to what we want. Put it back over there. There we go. All right. And now hopefully when I make changes, it'll snap there. Comments. There we go. Automatically. Are human readable messages embedded in code. Right? And we saw several examples of that already. Single line comments begin with a, what is that? What kind of slashes are those? 2 slashes. What kind are they? The guy looking that way is leaning forward, therefore they are forward slashes. Anything following that on the same line is ignored by the compiler. Right? And a common question is, well, should I put too many? Should I limit the number of comments or the length of comments? Because will it affect the efficiency or the size of the program? No, they are completely ignored. The compiler takes all the comments, throws them away, and completely ignores them when it goes to compile into binary. Comments are not preserved in the binary files. So how many comments should you make? Should you make them long? Should you make them short? You should Goldilocks them, right? I can't tell you what the perfect comment is. The perfect comment is the comment that 90% of the population reads it and they immediately understand it. And what do I mean by Goldilocks it? Don't want to make it too long. You don't want to make it too short. You want to make it just right. Exactly. Just like Goldilocks' porridge. Right? So, single line comments begin with a // Multi-line comments begin with a /* and end with a, just the opposite, */. Anything in between is ignored. Right? And then you also have what I did at the top of the program. You have doc-style comments. Right? See the headers of the example programs. Example programs. There we go. Spell it right. So this is a doc-style comment up here. It starts with, it's just a multi-line comment with more stuff, right? Extra steps. It is /**, and then you see that there's an entire vertical line of stars to align everything. That just gives a nice visual cue that everything in here is a comment, and it's a documentation comment. This is born out of, I believe, Java. They were originally called Java doc-style comments. And the reason that we like this kind of thing is because you can actually run external programs that take these doc-style comments and then produce other readable documentation, HTML pages, web pages, or PDF forms, or something like that. And if you write towards those doc-style comments, then you can see documentation for this thing over here, and it becomes clickable in that kind of stuff. Even in an IDE or something, an integrated development environment, it can become clickable. So adopt it if you want. I'm not going to force you to, because as long as you're doing it consistently. But if you're going to adopt doc-style comments, be consistent about it. Okay? And eventually, I'm not going to dictate style for one very good reason. Plenty of other people dictate styles. If you eventually get an internship or a job somewhere, they will have what's called a style guide. That is, it's an internal thing that this is how we expect you to write code because we want everybody to write code like this. And you'll be forced to adopt their style. Right? And whatever personal style you've developed and personal preference you've developed, you're going to have to throw that away and adopt theirs, because conformity is important in this case, because you're writing code not not just for a machine. You're writing code for other people. If other people understand your code, then it's way more maintainable. It cuts down on maintenance time. So you need to write good style, a good consistent style, and consistency is way more important than any particular differences between style guide. Google publishes a style guide. GNU publishes a style guide. There are dozens of style guides out there that are pretty much the same, though slightly different. And whatever style guide you adopt and go with, great, go ahead and do that. In fact, I'll show you a formatter later on. It's available in Canvas that you can. If you want to adopt somebody else's style, you can cut and paste your code, put it into this tool, stylize it, and it's called a beautifier. It makes your code beautiful according to some other style guide. Right? So again, I'm not going to enforce any particular style guide. I'm just going to enforce that you're consistent about it. Okay? So why do we have comments? Comments are designed, or supposed to be designed, to tell the why and the how of not the what. Right? Code should be self-documenting. Right? That is, the code itself tells you the what. Right? The standard here is that documentation, comments, should tell another person why you did something the way that you did it. The how, if you give me this input, I'll give you this output. Or maybe you're writing a complex integration function that uses, I don't know, Simpson's rule or something like that. You document that. We use the Simpson's rule for integration because it has nice convergence properties, whatever, right? Document the how and the why. The what, you should leave that to the code. And it's perfectly illustrated with this example up here, right? Those two comments that I put in there just to show you single line comments, prompt the user for input, read the input. Those are unnecessary verbose comments. Those should not be there in a real program. I'm only doing that here to show you what it looks like. The code itself, the printf statement, the scanf statement, that tells you what it does. Everybody, once you've seen a printf statement, once you've used a printf statement, a few weeks go by in this course, everybody will know what printf does. You don't need to document that because it's self-documenting. Everybody knows what printf does. But at the top, what does this program do? Yes, give me a summary. Give me a synopsis here. Okay? All right. So let's go ahead and look at some of the other things that we saw. Preprocessor directives. There we go. All right. I don't know why it's not. Okay, fine. So this thing up here, these three lines up here, these are preprocessor directives. There are two types. The preprocessor directives are directives to the compiler to do something and are executed before it starts compiling. Right? And I do promise that as we go along that this will be a little bit better. The only reason that it's not working right now on Atom.io is because the latest version of Atom introduced a bug, and I reported the bug, and as of, I think, 6 a.m. this morning, we acknowledged the bug, and they are working on fixing the bug. I have no idea when it's going to be pushed out, but hopefully it'll be fixed in the next couple of days, if not in the next week. And then we can go back to using Atom.io instead of this thing over here. But preprocessor directives, those things that begin with a hash, right? Hashtags are way older than Twitter, right? Hashtags go, in fact, Twitter's use of hashtags dates back to IRC. IRC used them before. Have you ever seen Slack? Has anybody used Slack? All right, a Slack channel, what does it begin with? A hash. Where do you think that came from? That came from IRC, Internet Relay Chat, which is older than dirt, right? So if you see a hash, it's just because somebody used it before in the context of computing, and they just stole it. Right? Slack stole it from IRC. Twitter stole it from IRC or wherever else it was been using. But it all goes back to the fact that we're stuck with a QWERTY keyboard, and we're stuck with the standard symbols that are on there. So if you want to say, okay, I need a way of telling the compiler to do something before it starts compiling, you're a language designer. Think you're Kernighan or Ritchie, the people who created C. All right, well, what do we do? Okay, well, hash is good enough. Let's use that, right? And no rhyme or reason to it. It's just because you're limited to the QWERTY keyboard, and they needed something to represent something in the language. And so they used hash here. Hash include, again, there are two types that we're going to be looking at. You can include, that is, bring in external libraries using the preprocessor directive include, right? Plain old English. It does what it says, and along with the library name. Right? And in the examples that we did, it was stdio, stdlib. Here's another one, another example. What else might you want to do if you're going to be doing stuff with numbers? What other tool might you have in your backpacks besides a computer right now? If you want to go to a math class, you've got a calculator. What are some of the special keys on that calculator? Sine, cosine, exp, tangent, all right? So Programming is no different. You want to be able to have a cosine button without having to program how to do cosine, right? Does anybody know how they would do cosine? Or sine? All right, well, you're going to be doing it in your third lab, right? I think the one that you do in your lab is nothing more than a Taylor series. So another example would include, let's include something that gives us a bunch of math functions. What do you think it's called? Yeah, well, to be consistent, it's going to be what? Not STD because it's not standard. There's a reason it's not standard. It's called math.h. The .h stands for header. Let me do something to get this behaving better. Text. There we go. Add some buffer space down there. There we go. Now it'll always come up. So you can include the math library, math.h, excuse me. That's a typo. There we go. And let me also increase the size here. There we go. Is that big enough for everybody in back? Yeah. All right, I'm not seeing any hands, so bigger, bigger, bigger. Oh, now I'm seeing OK signs. All right, it's good enough then for now. OK, so you can bring in the math library. The math library has sine, cosine, square root, and a bunch of other things that you can use, including constants like pi, e, and a couple of other things, so that you don't have to reinvent the wheel there. Cancel that. Right. And you can define what are called, what do I want to call them? You can define what are called macros using define. Right? Who would have thought you can define something using the keyword define? It does make sense. What are macros, though? Good on time. So has anybody ever heard the term macro before? Some business people at least, right? Some people have used Excel before. What's a macro in Excel? If you want to do a complex operation, you can record yourself doing it, so that if you want to do that complex operation with a push of a button, all you have to do is record yourself, like take this thing in this cell and copy it over here temporarily, add it to this cell, and then put the result over here and then delete everything. Right? You can do that in what's called a macro. You can record yourself doing it. You can program Excel to do it for you. Right? I don't know what it stands for, what the etymology of that word is, but a macro is very similar in C. A macro is nothing more than a preprocessor directive that, for example, anywhere, I'm telling the compiler now, anywhere that you see KMS underscore per underscore mile, replace that with this numerical value. So what the preprocessor does is it goes through your entire program, says, oh, well, there's one instance. It takes this and does a cut and paste of the value 1.60934. This is why I said it wasn't really a variable. It's a macro. This value here will be, these letters here will be replaced with this number. And it's done for a couple of reasons. One, convenience. I only used it once in this program. But what if I were using it twice, 3 times, 4 times, 5 times? And if I didn't use a macro, what would I have to do? I would have to take the same number, cut and paste the 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 number. What if I want to now be more accurate? What if I don't know what the next decimal in kilometers per mile is, but there is another decimal. I was only accurate out to 5 decimals. What if I wanted to be accurate out to 6 decimals or 7 decimals? If I use the same mysterious number in 5 or 6 or 100 different places in my program, guess what I have to do? I have to change it in 5 or 6 or 100 different places in my program. Or if I use a macro, then I can change it in one place, and it's magically changed everywhere else by the preprocessor for me. Right? So a very good design thing. Again, what is it called? DRY. Don't repeat yourself. Don't repeat the same number over and over again. Give it a human-readable designation, and then have the number in one location. Okay? A macro is essentially a cut and paste operation. It allows you to define essentially constants. There are other. It's not really a constant because it's not really even a variable. So a macro essentially allows it does a cut and paste operation. What else did we see? The main function is always the starting point for any executable program. All right? You need it. If you don't have a main, you just have a library. That math library, there's no main in the math library. It has sine, cosine, square root. The standard input-output library has that printf function, that scanf function, etc. So those are not starting points for a program. Those are other functions that you can use in your program, but it's not an executable. It's just a library. It's an object file sitting somewhere on the system. Okay? Again, for now, ignore everything else. That argv and argc, those are command line arguments. Ignore them for now. Other syntax and punctuation. Punctuation. There we go. What did you see? Let's go back to the program up here. What is punctuation and formatting in English? I've got English, you've got words. Words are made up of characters, delimited by spaces. And so you've got characters. Characters form words. Words form sentences. You've also, and in English, you end a sentence with a period. We have kind of the same thing here. How did we end our sentences? Semicolons, right? So semicolons end every executable line. Okay. What other punctuation did you see here? Again, let's go back up. What? Percent. Okay, those are placeholders. So placeholders in printf and scanf, right? Using the percent sign. All right. What else did we see? Commas. All right. Commas delimit arguments. And let me go ahead and italicize arguments because that's an important term, right? Where did you see them? You saw them between variables, right? Here's a list of variables. A list in English, right? This is a notice to all grad students, undergrad students, and postdocs. How would you write that in English? Comma, comma, comma. Right? And what about that last comma though? That's called the Oxford comma, right? And it's optional or not, whatever. But the Oxford comma is not optional in coding because there is no keyword and, at least in the C programming language. So if I had 3 variables, I would have 2 commas, right? And if I had 5 variables, I'd have 4 commas because you have to interleave them. Right? Where else did you see commas? In your functions. This is the format, comma, this is the argument. This is the format, comma, this is the first variable, comma, this is the second variable. Right? So commas all over the place to delimit arguments or delimit things, to separate things. What else do you see? Quotation marks. So double quotation marks. Double quotation marks indicate a string, a sequence of characters. Right? These are also called literals, right? Or string literal, I should say. All right. So you have an opening double quote, and a closing double quote. Right? You also have single quotes, and we'll talk about that when we start talking about variables, though. Okay. What else? Semicolons. So if characters create words, words create sentences, sentences create paragraphs. We have kind of the concept of paragraphs here. This is a function. Here's my main function. Well, what belongs to that main function? How did I start all this code right here? And you know that because I indented it. But how did I begin that function? How did I end that function? With curly brackets. So curly brackets denote what are called code blocks. Blocks of code. We don't call them paragraphs. We call them blocks of code. And just like English, you have code block, code block, code block. Sometimes you have code blocks within code blocks, and we'll talk about that when we actually get to, say, conditionals and loops. Right? What else? In general, white space does not matter, right? Except for styling. Right? Make sure that your white space is consistent. And there are several reserved or key words. For example, double or int or printf. Printf is technically a reserved word. It's reserved by the standard library. So if I go start naming my variables, first of all, I need to name them something descriptive. But I'm also forbidden from naming them certain things that are reserved by the language, like int or double. I cannot name my functions or my variables those words because they are reserved by the language itself. It has a special meaning to the language. Right? Just like in English, you can't use any word any old way that you want. Words mean things, right? And you can't just go changing the meaning of things unless you're a linguist or you want to start a cool new trend or something. Right? All right, what's an example? I've heard it only just recently. Mostly slang terms, right? I don't know. Have you heard of standing? All right. So I don't know how old that term is, but being basically a fanboy for something and trying to advocate for something, it's called standing now, apparently. Okay. Let's talk a little bit about variables before we head out. C is what's called a statically typed language. And all that means is that basically you have to declare a variable and its type before you can use it. Right? So you have to declare it up front. There's this variable called miles, and it's going to be a double. It's going to be a floating point number. And wherever I declare it after that, I can start using it. I can't use that variable before I've declared that variable. As an example, I'm going to go over to REPL here and show you that it won't work. So let's forget about printf here for a moment, and let's go ahead and create a variable. Int a. In general, a is a terrible. Well, let's go with miles. Int miles. Right? This is going to be an integer variable, and I'll go ahead and assign it a value of 10. Okay. Let's print it out. Printf percent a is equal to percent d is the placeholder for an integer. We'll get to that shortly. Miles. Right? So this will work perfectly fine because I declared the variable, then I used the variable. Right? What if I did it in reverse? What if I tried to print it out before it exists? Right? Well, it's already telling me that it won't work. Error, use of undeclared identifier miles. You're a compiler. You go top to bottom, left to right, just like plain old English. You start at line 6 and you see printf, print miles. Up to that point in the program, up to line 6, have you seen that variable yet? No, so you don't know what the hell you're talking about. Miles, what's that? All right, fatal error, I don't know what you're talking about. There's undeclared identifier. It is not a valid variable because you haven't declared it yet. You can't declare something after you intend to use it. That's what statically typed means. Right? Not only that, but once you declare it to be of a certain type, 10.5. Right? Now it's an under squiggly line here. Let's see what it says. That error has turned into a warning. Implicit conversion from double to int changes the value. Int is an integer. What's an integer? It's a whole number. 2, 5, -2, -5, 0. Those are all integers. 10.5, is that an integer? No. So I'm not allowed, bad things and unexpected things will happen if you try to force some variables to become some other types of variables. And in this case, I've said that this is an integer variable, but I've tried to force it to become hold a double value. It'll run, by the way. It's just a warning. Warnings are not fatal. It'll run, but what does it do? Is it 10.5? Nope. What is it? It's 10. What happened? Did it round up? No, 10.5 rounded up would be what? 11. It's called truncation. It takes that decimal value, chops it off and throws it away. I could have put in 10.99 here, right? Or 9999999. It will not get rounded up. It will get truncated and thrown away, right? I could put 10.0, and maybe even the warning will go away now, right? Well, 10.0, yeah, it's a 0.0, but it's still 0, so that's, of course, an integer. I'm OK with that, the compiler says, right? So that's what statically typed means, that variables have to be declared, and they have a type, and only that type. Their type cannot be changed. A variable's type cannot be changed, right, once declared. If you've created it and you've made it into an integer, it will only ever be an integer. If you made it into a double, of course, a double, 10.5, it can hold 10.5. It can hold 10.0, but you're not changing it into an integer because you could go back and add 0.5 to it if you wanted to, right? The scope of a variable is the section or sections of code. That is the code block in which it exists, right? Or is valid. Now, we haven't gotten to loops or any control structures that I can show you an example just yet. I can show you an artificial example, but I don't want you to throw you for a loop. So just remember that we're going to come back to scope. If I declare a variable, it's alive, right? And it's alive for that code block that I declare it in. If I go down here and this is the end of the code block, that's the end of its scope. Why do we call it scope? Well, look through a sniper scope or something like that. Do you see the entire world? Nope, you only see what you can see through the scope. So a scope limits the visibility of a variable to this code block in which it's declared. After that code block, if you go somewhere else, it's out of scope. We call it out of scope, and it no longer exists. So if I declare a variable a over here in this scope, and then I go over here to this part of the code, there's no variable a over here unless I declare it in here. And if I declared a variable a in this scope and a variable a in this scope, they are not the same variable. There are two variables now called a, which is perfectly fine because they're in completely different scopes, right? They live in different places. Just like we can have plenty of people with the same name. How many Chris's are there? What, really? There's no other Chris out there? All right, how many Johns are there? All right, so you're perfectly happy living together with the same name, right? Same as variables. You can have two variables with the same name as long as they live in different scopes, right? Nobody ever called me Chris growing up because we had like 6 Chris's in my class, and so everybody just called me Burke. Please just call me Burke. Don't call me Chris. I won't answer to it because it's been so long. Nobody calls me Chris, right? All right, so there are a few built-in variable types. Again, there are, depending on the version of C you're using, there could be a couple of dozen different variable types. I'm going to keep it simple. We're going to keep it simple, and we're going to restrict our attention to 3 basic variable types. There's an int, right? Is an integer that can represent values in the range, whole values in the range. And for this, I'm going to cut and paste this value because I'm not going to transcribe it correctly. There we go. Less than equal to x less than equal to. There we go. There we go. So it can represent any numbers from, and I don't have commas there, but that's 2.147 billion. So about negative 2 billion up to positive 2 billion. Every single integer in that range can be represented by an int variable. Why not beyond that? Right? Well, that's because it's a computer. This is a finite object. Right? My hard drive can only hold up to 500 gigabytes. My main memory, I don't know how, 8 gigs of RAM or something like that, it can only hold so much memory. Likewise, a variable is a finite object. If I said, well, you only have enough space to write 3 digits on your piece of paper, there's a maximum value that you can represent, 999. Now, what happens if you try to add 1 to that? I've only given you 3 spaces to write a number, 999. Add 1 to it. What do you get? 1,000. But what happens then? 999 becomes 0001. What happens to that 1? falls off the face of the earth. What are you left with? 3 zeros. That's called overflow, right? Likewise, if I only gave you 1 digit, right, then you could only represent a maximum of 9. When it goes over and you add 1 to it, it becomes 10. What happens to that 1? Well, normally if you've got a large piece of paper, you can just add it to the other end, right? Well, that doesn't work with a computer. If you only have so many bits, then what happens when you add another bit and it falls off the face of the earth? It's called overflow. What happens when you go the other direction? What happens if you start at negative 2.147 billion, ... and you subtract 1? You fall off the face of the earth. What happens is you actually come around to the other side. It's circular. So if I add 1 to 2.147 billion, the positive, it actually, because the earth is not flat, so if you fall off the face of the earth, where are you really going? If you go all the way to the prime meridian or whatever it is, do you fall off the face of the earth? No. If you go from the eastern hemisphere to the western hemisphere and you cross that prime meridian or whatever it is, you're just on the other side. So it wraps around to negative and you get weird results. Let's take a look. Miles, okay, I'll make it an integer. 2.147, let me go ahead and cut and paste this. So there we go. Not too much, there we go. In fact, it's giving me a warning, you can't represent a number that big. So if I do this, I get a nice result there, the same number that I made it as. But if I then later on I say miles is equal to miles plus 1, I'm just adding 1 to it. What do I get? I fall off the face of the earth and come back around to the other side. What's the other side? That's exactly the number that's over here. Right? It's circular. It goes back around to the other value because of overflow. Right? So just know that you have a limitation on integers. You can only represent a maximum of 2.147 billion and a minimum of negative 2.147 billion. You can represent 0. Yeah, that's perfectly fine. What happens when you need to represent, say, the U.S. national debt, which is way more than 2.147 billion? Now you need to bring in a library. They're called multi-precision libraries. If you need to represent an integer that is 50 digits, then you need to bring in an external library. And for C, the go-to library would be the GMP, I think, GNU's multi-precision library, right? Or you don't want to call it GIMP. For short, there's another library called GIMP that we'll actually take a look at later on, right? So those are integers. The other one are doubles, right? Or double, I should say. A floating point number giving you about 16 to 17 decimals of accuracy, right? And we call this decimals of accuracy because there are going to be 16 digits. It doesn't matter if you write down 16 digits. Write down pi, 3.14159. You can move the period and make it so that it's 3.14159 times 10 to the 100, which is an extremely huge number, right? You can make it so very, very small, 3.14159 times 10 to the negative 100, which is an extremely small number. It's still positive, right? We call that what? What do we call this when we do that? What if I do something like this? 3.14 times 10 to the, 24. Right? What do we call that? Scientific notation. That's exactly what a floating point number is. It's called normalization, that you take this number and you normalize it to scientific form so that it's no more than 10, right? That it's a 0 through 9. And then you simply move the decimal point to where you want it and put the magnitude over in the 10 to the power whatever. Computers do that, but they don't work in base 10. They work in base, remember, 2, binary. And so, but it's the same basic principle. Instead of a 10, they'll have a 2, and everything else will be represented in binary, but the decimal will be shifted. Or what's another word for shifting it around? Imagine that you're on water here. What is it doing? It's floating, right? And so it floats back and forth, and that's why we call them floating point numbers, okay? Just understand that it is basically scientific notation. It is essentially scientific notation, but in binary, right? Okay, we might talk about that a little bit more detail later on. But the big takeaway there is if you have a whole number, use an integer. If you have a fractional number, use a double. And understand that both of them have limitations. An integer, you can only represent 2.147 billion, positive, negative. A floating point double, you could only have about 16 decimals of accuracy. If you need any more than that, then again, you're bringing in a library to do it. Okay. And the other one that I want to talk about is a char. So what do you think char is short for? It's a single character value, right? In fact, it's an ASCII text value, right? ASCII, I forget what it's, oh, here, we'll end on this. Let's go ahead and do a Google search. What does ASCII stand for? American Standard Code for Information Exchange. Very, very old. What does it look like? Well, you can go to ASCIItable.com. And I'll zoom in here because that's terrible. But it's very, very old. It's English, American-centric. It's in the name, ASCII. The A stands for American. But it is the standard for all computers now because it was the first standard to be adopted. Every English language letter, both capital and lowercase, as well as basically anything on the QWERTY keyboard, has a numerical value according to this table. For example, capital B, the first letter in my last name, it has a value of 66. If you were to convert that over to hexadecimal, it would be 42, octal, and then HTML escape codes, whatever. This table is well designed. What do you see in a pattern in that in this column right here? What order are they designed in? Alphabetic order. Not only that, but capitals versus lowercase, which comes first? Capitals. What about special symbols like a space? Do you see where that is? Spaces come before all letters. Certain symbols come before other symbols. For example, these are not numbers. These are the symbols for numbers, and they're in order. 0 comes before 9. Who would have thought that, right? It's very well designed because this is called lexicographic ordering. It's not dictionary ordering. And so don't think of it, I know you said alphabetic ordering. Technically, yes, if you're only looking at single characters. But later on, we'll take a look at what it means, what's the difference between lexicographic ordering, ASCII text table ordering, versus dictionary ordering, okay? For example, 124 comes before 12 in lexicographic ordering. Wait, is that right? Comes before 9 in lexicographic ordering. It's not in numerical ordering, and so you can be tripped up by that kind of stuff. And we'll take a look in detail later on. But there are even non-printable stuff, right? What about an n-line character? Do you see where that is? I forget where it is, too. Where is it? It should be like low. Where do you see it? Oh, there it is. Line feed, new line. It has a value of 10. New line characters come before all this other stuff over here. And so a char value can hold any one value. The way that you do that is, let me go ahead and create a variable for my initial, my first initial. My first initial is going to be a capital C. How did I do that? How did I refer to a single character? Single quotes. So double quotes were what again? Strings, multiple characters. Single quotes are for single characters. Okay? Any questions? Otherwise, reminder, no class on Monday because of Labor Day, right? I fixed that in the schedule. This one will be posted soon after. If you just recently registered, make sure that you get caught up. Make sure that you're doing Lab 1 before tomorrow, and make sure that you're showing up to your hack tomorrow with your first real meaty assignment.